Welcome to all participants and observers of the Air PPM Hackathon. Today, we are honored to present a lecture by Professor Goutam Chakraborty from Iwate Prefectural University, Japan, and Mandapalli Institute of Technology and Science, India. His talk, titled Chaotic Time Series and Air Pollution Model, will explore the role of chaos theory in understanding air pollution dynamics.
Hello everyone. I'm very happy to be part of this hackathon, and I'm very happy that I'm invited to say something about the environment. The title of my talk is Chaotic Time Series and Air Pollution Model, and I'll take around 15 minutes. So my name is Goutam, and I have two affiliations, Iwate Prefectural University in Japan, that is located in north of Japan. And presently, I'm a dean in Mandapalli Institute of Technology and Science in India. Okay. So today's agenda is like this: breathing clean air. It's a dream for billions. Why I call it a dream? Because billions don't get clean air to breathe. The next item is air pollutant concentration, APC in short. And can you predict for instantaneous changes? Okay, I'll explain that in later slides. And we'll see that in APC, there is a chaotic variation. Its modeling is important to explore the cause, and its prediction is important to save lives. So I will first give an example, and that's not from India or some African country, it's from London. Preliminaries about chaotic time series modeling, how we do that, and what are the challenges, especially for APC modeling. And finally, I'll conclude with the humble, what I should say, pray. So this is a fact. Breathing clean air is really a dream for billions. And according to WHO, 92% of the world population, they don't get safe air. And the air they breathe, that pollution level exceeds WHO safe limit, which is quite surprising. And the map, you can see that the green areas are okay, but the yellow to red and dark red, they are worse. Okay. As we all know that breathing problem, lung cancer, heart disease, strokes, all these emanate from breathing, pollutants available in the air. As you see that, okay, like India, uh, most part of the China and Africa, South America, they are quite, pollutant is quite heavy. But you see that even south of UK, most of the Europe and are also not escaping this. If you see like this Iberia, this vast area in Russia where no people live, Scandinavia is good. Canada also almost it is unpopulated, so there is good. So population brings a lot of pollutants. Okay, and the main reason is that we are not conscious about that. And this picture is from 2016, and I'm sure the present situation is much worse. Okay. Air pollutant concentration, or in short APC, there are two types. One is indoor air pollution, which is actually worse. I have seen in Mongolia, in Ulaanbaatar, every home in winter, they heat and cook with burning woods, and inside the home, it's gas chamber. So cooking and heating are the main reason for air pollutant inside the home. And outside there are power plants, factories, vehicle exhaust. So these are, in all mega cities, we have this type of pollutants. Now the air quality is measured with respect to the small airborne particles. By big airborne particles, actually we can filter out by using mask and all, but very small airborne particles are more dangerous. PM 2.5 are particles with diameter less than 2.5 micron. And this can enter our blood vessel, and through blood vessel, it can go to the brain. And of course, it can create cancer in many parts of the body. And PM10 are particles with diameter less than 10 microns. They consist of dust and all those small particles, but they deposit in the lung and finally cause respiration trouble, lung cancer, and many others. So this is very common. I mean, my hometown is Calcutta. It is very common. Respiration trouble is almost with everyone. Okay. Now, by modeling this pollutant concentration, particle concentration, we can investigate their sources. I mean, depending on the changes and if you have all the information of the environment and what are the activities going on, we can correlate them and we can reduce it and mitigate them. And we can also take preventive measure to save lives. When there is a large number, actually for many dynamic phenomena, if there are large number of factors governing the dynamic system, it exhibits chaotic behavior. Okay, and you can see that in heart rhythm, in weather pattern, and many other. I mean, in share market, because share market is dominated by many factors, and they do not interact with some correlation. And in such a case, the combination creates a chaotic dynamics. It is chaotic dynamics. The chaotic behavior is observed only at very high resolution. That is one important point, and that's how the data collection is governed. To emphasize or to characterize, to find the characteristics of the chaotic part, we have to find the embedding dimension and the time delay, and the detail of which we'll discuss later. Okay. So in the beginning, I told you that I'll give you an example. So here the data is collected from London's Honor Park monitoring station. Okay. On the right, you will see that the concentration of different, pollutant, chlorine is a pollutant, heavy metals, and those are there. And the black line shows the PM 2.5, level of PM 2.5. Now, this is the average. I mean, this is the overall pattern of changes. But in the next slide, if we look more closely, we'll see it looks like a random. Okay. Now, we are interested in this randomness of the change. And we'll show, we'll not show, someone has already researched that it follows some chaotic pattern. And using chaotic model, we can predict or we can model this series. Okay. Now, there's some preliminaries you should know about chaotic time series modeling. First of all, you have to ensure that it's really a chaos or a random or a mixture of two. Okay. If it's completely random, we cannot predict anything. But if it is chaos, but some portion of it is random, then also there are methods to eliminate that random part and then extract the chaotic part and model it. For most of the natural phenomena, there is a slow variation. For example, we have seen there is a slow variation, and slow variation part can be removed. There are many ways to do that. And the tiny small variations or high resolution variations, we have to extract, and then we have to try to model it. We have seen this type of fluctuation in heartbeat. Heartbeat, there is a periodic changes, we all know. But over that, there is a very small, high resolution chaotic changes, dynamism. Actually, this is needed when we say there is a cancer in the heart and you want to treat it by ray, and the ray should pinpoint only at the point of cancer, then we need to, ensure that these chaotic small changes are taken care of so that the ray exactly burns the cancer part and not the healthy tissues. Okay. And there are other phenomena like population dynamics of species, weather pattern, concentration of APC, which is our, topic of interest today. And they all show some chaotic changes. Okay. And yeah, we say regular chaos when it is predictable. Okay. Now to check whether it's chaos, chaos has some regular chaos has some properties: self-similarity, scale invariant, fractal. The original signal and the aggregated signal have the same statistics. So you know that if the signal is random, and then if you aggregate it, if you M aggregate it, then the variance is reduced by M, by a factor of M. But in case of chaos, the variance of the aggregated signal and the original signal are the same. So this is one way of verifying whether it's a chaos or random. Okay. Now, if you see the distribution, then chaos, random shows a Gaussian type of distribution, but chaos shows a log normal. And it is skewed towards the right with a longer tail on the right. Okay. And another very easy or commonly used is Lyapunov exponent. For chaos, the Lyapunov exponent is positive, and that's another way to verify whether it's chaos or random. Now, when considering the APC, we have the following challenges or difficulties, I should say. As I told you earlier, that chaotic dynamics to ensure to extract the chaotic dynamics of the system, we need data at a very high resolution. It's not a difficult problem now because we have very good sensors which can take data every probably microsecond or 100 microsecond like that. It's not difficult to collect data at short intervals. Okay. Whether we need at that interval or a less interval, longer interval is okay. That is called the time delay. We'll come to that in the next slide. But basically, only if you have data at very short interval, then only we can proceed. Okay. There is a way to find what interval of the data is suitable to make the model. And so that is called the time delay. So say suppose you have data at every 100 microsecond, but you can find that a data at 1 millisecond interval is good for modeling. And that what is a optimum interval which is suitable for modeling, we can find it by using mutual information. Again, I'll come in the next slide, I'll explain it. But mutual information gives the time delay, which is proper for modeling the chaos. And as I told, I think mentioned earlier, that APC data will always have a slow varying component, which we can eliminate very easily. There are, umpteen number of ways to do that. Yeah, and I'm not going into the detail of how to separate between the random part of the data and the chaotic part of the data, but please believe me that there are ways to do that. And this is again a problem, especially with APC, that it may consist of multifractal characteristics, not a single model, but we may need two models to, amalgamate two models to properly model the APC. Okay. Now, coming to the time interval, we also call the time delay. So you have data at very short intervals, and those data, I call it x1, x2, x3, x4, like that. And if I mention that we have 600,000 data, so we have x 600,000. Okay. Now, we made a series with x1, x2 up to n minus t and 1 plus t. So these two series A and B are delayed by a time interval of capital T. Okay. Now we change the capital T. So we change the capital T and see the mutual information between these two series. Mutual information is a very effective way to find many things like gasoline price in your gasoline station and international gasoline, crude price. They have a mutual information relation, but there is a delay. Now you have to, if you want to find the proper delay between the international price and your gasoline stand price, then you can use the same method. Okay, mutual information. Now, in this case, the mutual information, of course, the mutual information is very high if capital T is almost zero. Okay, but as we increase the capital T, the mutual information slowly decreases, and it takes the nature of this curve is something like this. The first minimum, the point at which the first minimum occurs is the time delay. So here, if you see, the first minimum occurs at a distance of, at a time interval of capital T. So capital T is the delay. So instead of using the high resolution data, what we do is that we take x1 and then x1 plus capital T, then x1 plus capital 2 into capital T, 3 into capital T, like that. Okay. So that is the time series which we'll use for modeling. And this is a, real example. Of course, this is a synthetic data. We call Lawrence data. And Lawrence data is used in many experiments. Or, if we give some theory, usually we start with experimenting with Lawrence data. And here you see that the mutual information slowly decreases, then increase and decrease and increase like that. But the first minimum is here. So this is the time delay. So from the original data, we take out data at these intervals and then use that data for modeling our dynamic system. What are the challenges? So the agenda is saying, depending on the application, we need very short, and long time prediction. For long time prediction, we don't need a chaotic model. Okay, we can use some autoregressive model or whatever. But for very short or probably for short time prediction, we need this chaotic model. And we need to have a close coordination with some environmental expert to see what are the environmental phenomena that we can correlate with our model, so that we can find the reason for high pollutant particle in our air. Okay. The other important aspect is the embedding dimension of the dynamic system. And by embedding dimension, we mean is that, okay, so this is we are trying to predict xt plus d, considering all the previous data like xt minus 1, xt minus d minus 1. If you remember in autoregressive model 1 means we can predict the present data based on only the previous data. Autoregressive model 2, you can predict the present data with respect to the 2 previous data. Here, we are trying to establish we can predict t plus d depending on what happened previous d instance of time. T minus 1 up to T minus 1. Okay. So this is this we call the embedding dimension. Now we have to properly find, for example, for autoregressive model, we have to properly find what is the model dimension. It is AR1 or AR2 or AR3. Here also, this embedding dimension will tell you how many previous data you need to model. And now once you how to do that, I'm coming, probably I have one slide for that. But once you know the D, once you know how many previous data you need to predict the next one, then you can use somewhat. You cannot express analytically, but you can train models like support vector machine regression or recurrent neural network, where the number of inputs is D, and then you model and predict the next one. Okay. So To find the embedding dimension, we use a method called false nearest neighbor. Okay. So what is false nearest neighbor? I just let me check. Okay. I have some slide to explain how to find the false nearest neighbor. But before that, I'll show you some nice picture. And here, the embedding dimension is 2. Okay, so if you plot xt versus xt minus 1, you will see that the data moves along, repeats on a path and around some region, some locality. Okay, so this for this example, these two are called the attractor, or sometimes called strange attractor. Okay, and this I draw just like that. But if you can take the Lorentz data, and here actually Lorentz data is very similar to some weather model. So that's why I have, this picture is coming here. So Lorentz data has embedding dimension of 3, and if you plot, you can see that actually there are 3 strange attractor, one here, and one here. Okay. And how to find the strange attractor? So what we do is that, suppose we have, we make vectors of dimension d. Okay, so vectors of dimension, say d equal to 3. Then x1, x2, x3 is a vector. Then x11, x12, x13 is a vector. So we take all combinations of length 3 vector and find the mutual distances and find the minimum distance. So that is the minimum distance in 3 dimension. Now we go to 4 dimension and then we find the minimum distance. If from 3 to 4, the minimum distance jumped a lot, it is much more, then we ensure that, okay, 3 is not the proper dimension, 4 is the proper dimension. So we go on doing that, starting with 2, 2 to 3, 3 to 4, 4 to 5, like that. And when by increasing the dimension, we really don't change the distance, minimum distance much, then we ensure that, okay, D is fine. We have reached the proper D. And for most of the cases, a embedding dimension of 3 or 4 is sufficient. So there are two things not to worry about. So one thing is that you don't need to search a lot. By 3 or 4, you will reach your point. And secondly, if you use a embedding dimension more than the proper one, more than the minimum one, then also your prediction, your model will work fine. Okay, but of course, if 3 is the dimension and if you use 4, you will get a good model, but your model training and everything will take longer time. So that's why we usually try to find the minimum of the embedding dimension. And I think there are many researchers where they just use 3. 3 is a very common embedding dimension. Okay. So these are the basics how you can make a model. But this is only a very small part of the whole story, because you have to collaborate, you have to work with some environmentalist to know the reason, or someone who is aware of the activities, environmental activities around the region. We need to work with them to explain what is happening. Okay. And finally, I conclude with these things. Mostly, I pray that to achieve and maintain a clean environment, we need to educate people about the close relation between clean environment and public health. Okay. To educate people to love the nature. This is very important. I have seen countries where people very much love the nature, like Japan, Switzerland, a part of Scandinavian countries. But there are many countries where nature takes the least priority. To train the whole population to actively participate in this effort, to have political motivation, which is lacking in many parts of the world, to be able to raise some research funds. Place where the environment is a disaster, we have seen this type of properties. We do not have proper overall education. education is lacking, conservation of nature has very low priority, and especially there is no political will. Okay, with that, I conclude my talk, and thank you very much for your attention.
Thank you for joining us for this insightful presentation by Professor Goutam Chakraborty. We hope it has provided valuable knowledge on how chaotic time series modeling can contribute to better understanding and predicting air pollution. If you're interested in exploring more, visit www.rppm.org for additional resources and to register for the hackathon. Your ideas and solutions could make a real impact. Best of luck and see you at RPPM.